Hello, everyone. Welcome to Algorithms Live. This week is actually a double week for Algorithms Live. We had some technical issues with last week with the Hangout, getting it to set up, getting a live stream going. So it's the first time I've actually had that issue, and I looked into possible causes, and I've got a few workarounds now if some kind of issue like that happens again. So this isn't the episode 7 we had planned. The episode 7 was supposed to be with Makoto Sojima, and we were going to talk about @coder, but now that's on this Sunday. So be sure to tune in this Sunday. It should be a great episode. We've got a lot of cool things to discuss, and a lot of you ask questions or through the blog or various places, and we're going to try to work through all those questions. It'll be a really great episode. So I hope to see some of you tuning in on that. But today I decided I wanted to test the system again, make sure we can do a live stream. And I also wanted to talk about this problem on Steiner trees. I came up with our own ICPC training here at UCF on Saturday practice. And I just decided I think this would be a really good topic to go through. Not really a lot of material on Steiner trees for competitive programming that I've seen. So I thought it would be something interesting, a little bit different, and a good Friday episode for this double episode week. So let's start off with like what Steiner trees are and what the problem we're trying to solve is. And what we have is, we can describe it as a graph problem. There's other versions of it that aren't on graphs, but the most common variant is going to be on a graph. So we have some kind of a graph here. It doesn't really matter what the graph looks like. And what you're given is the graph, but then you're also given marked nodes. So I could say that this node is marked, this node is marked, this node is marked, and this node is marked. And you could have weights on the edges. The graph doesn't have to be unweighted. It can be. And the idea is to get the minimum cost connected set that joins all these nodes. And it's pretty easy to see that if you ended up getting something that connects all these nodes by taking edges, it's going to form a tree. And so here is potentially one connecting set. I don't know what these costs are, but I just want to show you kind of how the joining could look. You can look something like this. And what you have here is all the blue nodes, the blue marked nodes are connected. They can reach each other with a path from one to the other. But then I'm also adding intermediate nodes into the middle that I can optionally take to form my connected set. So I could have just as easily had picked a different path to form my connected set. I could have gone over here, and I could have instead connected it this way. So there are multiple trees that could form this connection. And one of the things that makes this problem pretty hard is you don't know what the intermediate nodes are going to be to form these connected regions. They could be anything. And so we want the minimum cost to join all these connected regions. These blue points right here that I'm marking with a star, they have a special name when you're talking terminology of Steiner tree. So these ones are called terminals or terminal points. Historically, I used to call them leaves, but that's not a very good name for them. So if I start using the word leaves, I really mean terminal. I'm trying to break that habit for myself. And there's also a special name for any node that has some kind of branching off. So you'll notice this node doesn't branch off in terms of the Steiner tree, but this middle node right here does. And this has a Steiner point. Get to that in a second. Steiner points are really useful in some of our analysis on thinking about the branching factor of our solution trees. It's going to be one of the things we're going to use to help speed us up and get a really fast solution. Another thing I want to point out is if you end up taking all the nodes and you require them to be terminals, so every single node in the graph, you just make it a marked blue node. There's a very well-known problem that most of you will be familiar with called minimum spanning tree. So you can think of minimum spanning tree as a special case of Steiner tree. And Steiner tree is just a different variant where some of the nodes you have to take, not all of the nodes. And it turns out just by changing this restriction of not having to take everything, this problem becomes a lot harder. In fact, if you haven't looked at this list on Wikipedia, I suggest you do. It's really useful for just computer science in general, but also for competitive programming. It's one of Karp's 21 NP-complete problems. And I urge anyone that's training for contests to take a look at what problems are NP hard or NP complete. So the optimization version of this problem, like minimizing the cost, this is going to be NP hard. And so it's good to know which problems are NP complete, which problems are NP hard, because most of the time, unless P equals NP, then unless P equals NP, we're going to have a really tough time solving this problem efficiently. So you're probably not going to prove P equals NP in the middle of a contest by solving one of these problems in polynomial time, so it allows you to think about it exponentially. So we did get a question already from about Steiner tree, and the question is, can't we just single source shortest path from all terminals, make a new graph of terminals, and apply MST, or did I get something wrong? So one of the problems with that is you're not necessarily connecting all the nodes in terms of your MST. So there's intermediate nodes that could be up here, or there's intermediate nodes that can be over here that may or may not be in your MST or in your Steiner tree. And you need to make decisions on that. That's the part that's making it really hard. And so you also don't know what your Steiner points are going to be. So that's the branching factor. So you could use single source shortest path to branch out to these Steiner points, but then we end up getting some problems. So part of the decisions that are really hard are picking what your Steiner points are, or picking what the form of the tree is and what those intermediate nodes are going to be. So that's really what makes this one hard. Okay, so it is NP complete, the decision version of this problem, and it is pretty challenging to do. But the comment was on the right track for one of the algorithms that we're going to try. So this one is exponential. So it turns out I think what makes Steiner tree problems pretty unique is you can get away with a small number of terminals. So if you have a small number of terminals, even if you have a large number of nodes, you can probably do Steiner tree. And so the very first algorithm we're going to look at is we're going to look at the case when we have very few terminal nodes, and we're going to make assumptions about the structure of the reduced tree. I'm going to call this thing a reduced tree of our Steiner tree. So a reduced tree is going to be us observing what the tree looks like if we only contain Steiner points and terminals, and consider everything else as paths between Steiner points and terminals. So going back to what we were considering originally, if we were given some kind of graph, we're going to draw out a graph here. Just any kind of graph. The very first thing I'm going to do is I'm actually going to mark these terminals, and then I'm just going to run single source shortest path to all the other nodes. So that was very much on the right track. Here, I'm not going to consider a weighted graph, so you'll just kind of see single shortest path at work. And so what I'm going to do is for every single terminal, I'm just going to compute a table using single source shortest path that tells me how far that terminal is from everything else in the graph. So in other words, I'll know how far, I'll be able to quickly compute for some terminal node that I'm trying to analyze, like how far is that from everything else? And I'll do that for each terminal. So if T is my number of terminals, so I have T terminal nodes, then I'm going to run T shortest path. So single source shortest path. So you can just run Dijkstra's, or if it's unweighted, you could run BFS, something like that. And I can just compute a distance matrix for every single one of these. So if I'm running Dijkstra's, typically what you have is you have an E log V Dijkstra's is one of the most common ones. A lot of people implement it as E log E Dijkstra's with a priority queue. So if you don't have Fibonacci heap, or you're not using a tree set, or you're not using an interval tree or something, or a segment tree or something, then it's probably E log E. But most of the time, this is actually faster in practice than the E log V, true E log V shortest path. Maybe I'll give future algorithms live, and I'll talk about why. It's kind of interesting. But we'll leave that at the table now. So we're just going to do this pre-comp. And what I'm going to do is I'm going to make an assumption about this form of the reduced Steiner tree. So what I'll do first is imagine these are terminal nodes out somewhere. And so I'm only going to take a glance at terminal nodes. And I call this algorithm the Spider-Man algorithm, because I'm going to make some assumptions about the structure of the reduced tree here. And you're going to see this is very much like Spider-Man with the way this algorithm works. So I'll call it Spider-Man algorithm. That's our first attack on Steiner tree. So the way this works is, imagine I start an arbitrary terminal node. And what I'm going to do is I'm just going to start walking. And then at a certain point, I'm going to decide that something is a Steiner point. And I'm going to try to connect one of my terminal nodes that are out somewhere else and do that at the minimum possible cost. So here's the way this works. I can just query my table of single source shortest path and connect this node without actually moving from my terminal node. So I'm going to make that assumption. I can just make this connection. Okay, then I'll walk out a little bit further, end up going out to another node. Maybe I'll connect it to two of these terminal nodes. And again, this is just going to be the cost coming from one of those single shortest path tables. So I have T of those, and I can get this cost very easily. And I walk out to maybe a new terminal node, and I'll connect two more things. All right, so when I say walking around the graph and then hooking things up, what I'm doing is I'm basically running a modified Dijkstra's. So I'm doing a modified Dijkstra's. And then if you've ever done a modified Dijkstra's before, you know you augment your state. So my state is what node I'm at. So this is the node I'm at I. So it's a lot like dynamic programming, except instead of a dynamic programming state, I'm considering it a state node in my search for my shortest path search. And then what I do is I keep a mask. And this mask is which terminals I've already connected. So what I'll do is I'll run this Dijkstra's from one of my terminal nodes. I'll walk out to a certain point. So my transitions on my Dijkstra's, I could be at a certain node. I could try moving to all its adjacent neighbors with some cost. That will be a walk in Dijkstra's. So it's kind of like Spider-Man walking around. And why this is called the Spider-Man algorithm is every time I go to hook up one of these terminal nodes, it's basically like I'm shooting web and I'm just like hooking myself up to various places. So that's why I call it the Spider-Man algorithm. It's kind of a visual way of representing how this works in Steiner tree. So let's analyze the restrictions on Steiner tree and what it can do on this particular algorithm. This only handles very special cases of reduced trees. First off, notice we can't ever branch and hit 2 nodes. So let's say I have 2 terminal nodes down here, and I run my Spider-Man algorithm. Spider-Man's web can't branch off and hit 2 things. It can only directly attack something. It can't switch and then branch off and then go into 2 different areas, and that ends up being a problem. So this kind of graph like this, where I have a really long path and I have single edges branching off of it, or in this case, single paths branching off of it, has a special name. It's called a caterpillar graph. So if it turns out, I think that's AR, maybe ER, I don't know. Not sure how to spell caterpillar, but it's basically a tree with limited branching factor. So you're always going to be able to find a nice long path on a caterpillar graph, and then everything else is going to be a path off of it. So this path itself could have a really big branching factor. It could branch in multiple places, but everything that's coming off the graph ends up causing a problem. So I said this algorithm will work on Steiner trees, yet it doesn't handle all classes of tree. It only handles special trees, these caterpillar graph trees. So when does this algorithm start to break? Let's try to analyze that, because that'll be interesting. So the first thing I'm going to do, trivially, if I just run Dijkstra's from point A to point B, if I have two terminal nodes, then it doesn't break, because my modified Dijkstra's just turns into regular Dijkstra's, and it ends up working out. The next class of graph that I might come across is I could have 3 terminal nodes. And it's fairly straightforward. I could walk from here to here and then stop at some intermediate terminal node. So I walk out to here. And then I branch off and get this one. So I have a long path, and I have a single branching factor that leaves me. A single path that branches off from this terminal node, doesn't go anywhere else. Perfectly fine. So for 3 nodes, I'm also good. So if I have 2 terminal nodes, 1 terminal node, that's trivial. Cost is going to be 0, so I'll ignore it. 3 terminal nodes, still good. You get out to 4. And so now this is where you start thinking about Steiner points. You want to have as maximum branching factor as possible. So I'm actually not going to prove that this is the worst case, but it happens to be the worst case. Here I have branching factor 4. It branches into 4 pieces. And I can see that this reduced graph for my Steiner tree graph is a caterpillar. I walk out to here, and these 2 edges right here are a single branch that leave this graph and don't do anything extra. So it's still meeting the requirements of being a caterpillar graph, even though I walk from somewhere else. So if we get out to 4, it still works. 3 works. 2 works. What about 5? So 5 is kind of interesting. This is where things are starting to get strange. I could do is I could write out a few of these nodes. This happens to be the worst possible case for 5. So I end up having 2 Steiner points here in the middle, get a branching factor coming off, branching factor coming off, and then an intermediate Steiner point here, and then a branching factor coming off. Now, it doesn't have to be any, like the spine of the caterpillar doesn't have to be every path between a node. And you'll notice if I start from this node right here, I end up not having a spine of a caterpillar that works. So if I try connecting it here to here, notice there's branching factor here and I'm in trouble. I can't, that's not a web I can sling with the Spider-Man algorithm. But if I come from this node and I get pick this diameter, I'm still good. Notice every single one of these paths leading off to me, I can just query the table from single shortest path, hook up those terminal nodes, I still have an answer. So walking around, I'm still good. There's no problem here. So the way you get this to work in terms of your Dijkstra's is you don't BFS with the modified Dijkstra's from just any terminal node. What you do is you start your BFS for Dijkstra's at every terminal node, because you don't know which one is going to be the best one. And your quit condition is when you get your mask full. So as soon as you find the minimum cost where your mask is full, then that's your answer you return, and that ends up being your Steiner tree. Works for 5 nodes. What about 6 nodes? This is where it breaks. You can't do 6 nodes in this algorithm. So if I have 6 terminal nodes, I'm going to have to do a different Steiner tree algorithm in order to solve it. So here's how this works. I'm going to pick some Steiner points inside my tree. I'm going to pick a Steiner point right here, hook it up. And these are the paths. So this is my reduced tree. And now you'll notice this form of tree is very bad for me. I can't pick any pair of terminal nodes on this tree without having a branching factor at some point. So there's my problem. I really can't do better on 6. So the Spider-Man algorithm works if the number of your terminal nodes, we'll call n term, is less than or equal to 5. That's when the Spider-Man algorithm works. It's actually a pretty fast algorithm because you're doing, the runtime is in terms, let's say T is terminal nodes. And I'll just do classic. N is nodes in my graph, and M is edges. We can analyze the runtime of Spider-Man. The pre-computation is T Dijkstra's. Algorithms just run all at once, so M times log N plus, and then what I'll do is I'll have a 2 to the T M log N algorithm. It's also 2 to the T right here. So actually bring that factor out, so it ends up being T times 2 to the T times M log base 2 of N. That's the runtime of my algorithm. So not terribly slow, but still pretty bad. You can generally, if your number of terminals is less than 5, you can typically run this on a pretty big graph. So even though it's an NP-hard problem, you'll just see the bounds are really big, and you're like, I don't think I can do something exponential. But because the number of terminal nodes is small, so if you're given less than 5 or less than 4 or whatever for your terminal nodes, you can run this algorithm and you'll end up computing Steiner tree. And it's mainly because every single Steiner tree's reduced tree is going to be a caterpillar graph. But once you get to 6, this doesn't work. So let's talk about how to attack the case when you have more than 6 Steiner nodes. Once again, we're going to be exponential on the number of terminal nodes. We're not going to be exponential on the number of nodes in general. So the way this works is we're basically going to do a DP. And here's the state of our DP. So we need a DP state. What I'm going to do is I'm going to form a rooted tree at one of the nodes in my graph, and then say that I've hooked up some terminal nodes so far. So I need 2 pieces of my state. I have to know which is the root node of my tree, and I need to know a mask And so my mask is going to be which terminal nodes I've hooked up. Yeah. So the size of my state, 2 to the n, whatever you're going to do. Okay. So I need to end up hooking these pairs of things up. So the idea works something like this. What I'll end up having is I'll have some rooted tree, some cost, and I've already hooked up some terminal nodes. That's going to be what's stored in my DP state. And then maybe there's some other tree in my graph. And it too also has terminal nodes hooked up. So what I'd like to do is I'd like to join the two roots of these trees. And what it'll do is it'll form some new rooted tree here and basically join these masks. So it's very brute forcey. Any tree you have can be formed by iterations of combining these terminal nodes. So let's take a slow example look here. So imagine these are my terminal nodes. So I have 5 terminal nodes. One possible combination is I could walk out to here, have this node walk out to here, and hook it up to be this is the center of my these two terminal nodes out here, there and there. And then I could do the same thing over here. Could potentially walk it out to this position. And this node right here is the root of this subtree. Maybe I go out a step further and hook it up to the root of this subtree. And then at some point, I could pair these two subtrees together with some cost. And that's the essence of the DP. So we're basically storing information of trees that we formed by hooking up terminal nodes, and that tree is rooted somewhere, so we can slide them around. So in order to do this efficiently, what we're going to do is we're basically, I need to be able to slide some node from where it currently is, whatever subtree I currently have, to another position in the graph. So I might have a terminal node here. It's all by itself. And I don't want the subtree rooted at that node for that node. I want it rooted somewhere else in the graph. So every time we compute some collection of terminal nodes that's forming a tree, what I'm going to do is I'm going to try sliding the root around. I'm going to try taking where the current root is and try moving it to a different place in the graph. So a way to do that efficiently is compute all pairs shortest path for the whole graph. So take what I currently have, pre-compute the all pairs shortest path. That'll allow me to quickly move where the root is at some cost. And then after computing any subset form of Steiner tree, I'm just going to move that root around by doing a for loop over all possible other nodes. And the cost of moving the root to be a different location is going to be the table from my all pair shortest path. So this is pretty easy. Just run Floyd-Warshalls. And that will be basic information. OK, so now we've actually rooted the tree at 2 different locations. So I may have joined these 2 trees, and these are my terminal nodes. And I may have joined these 2 trees at this node, and these are my 2 terminal nodes. But I may want to join those 2 subtrees at some intermediate node I. Well, because I'm pushing where that intermediate node I is, I will have considered moving the root of this node in both cases 2i and stitch them together. So it makes my DP for computing Steiner tree that much easier to calculate because I have exactly where the shared root is of my node. I just have to consider pairing up two subsets of nodes from scratch. And so that in essence is the algorithm. So let's take a look at writing some pseudocode for doing this iteratively. And I'll write a solution to this ticket to ride problem using this pseudocode in a bit. Okay, so for all subsets of terminal nodes, that's the first piece of our algorithm. So we just loop over all subsets of the terminal nodes. And then what we do is we loop over for all Yikes. There we go. So for all roots I, loop over that. Now we loop over for all subsets of mask. So let's look at what's going on here. This loop is going to form some mask of a subset of terminal nodes found. So there might be a whole lot of terminal nodes here that are going on. What I'm going to do here is I'm going to take a subset of that mask. So it might be 1, 0, 0, 1, 0, 0, 1, 1, 0. And that's a subset of that mask. It actually forms a partition of these terminal nodes, because I can end up having two halves. If I union them together, I get the entire tree. Here's what the partition looks like. It's basically everything that wasn't in the first mask is in the second mask. And so here's the other half of my partition. So I try stitching those two together. So I update the DP of I mask with the cost of transitions, cost of two subtrees. All right. And so once I've done doing that, I actually have my answer for DP rooted at I. So the node is rooted at I. And the mask is just everything that's connected terminal node wise. Now I can loop through all of their nodes and update DP of J mask using DP of I mask. And that's it. That's the algorithm in a nutshell. And I'll be coding this in a bit all the way through, but I just wanted to write out some pseudocode, give you an idea of what the runtime is. All right, so this subsets code here is going to be 2 to the terminals in runtime. This is going to be order n, because it's just going to run for every single root possible. This is subsets of subsets. So it looks like this is also going to be 2 to the t, but if I only explore the subsets, it actually amortizes to a really good runtime. So we'll get back to that. And then this piece right here is also going to be O of n. So if I just analyze the nesting loop of all the subsets, all the roots, and then all other nodes together, that piece of the big O is going to be n squared times 2 to the n. Now what I could do is I can ditch this other half right here and do my analysis on the other 4 loops. So I have subsets, I have all root nodes I, and then all subsets of subsets. So it turns out that that's going to be n times 3 to the t. Oh, yeah, this should have been 2 to the t, not 2 to the n. Oops. But everything else is looking good. So that's my new runtime. It's n squared times 2 to the t, and n times 3 to the t, plus n times 3 to the t. And you might be wondering why subsets of subsets is 3 to the t. So let's take a look at that. there's two ways we can prove this. And here's one way. So what I'm going to do here, here's a subset. Here's a subset of that subset. Okay? So how many pairs of masks exist? Well, we can look at the number of nodes that form right here. Okay? So the types of nodes we could have, it's not in the original mask, and it's not in the subset of the subset. It is in the original mask, but it's not in the subset of the subset. Or it's in the original mask and in the subset of the subset, but the only case we can't have is it's in the original mask, but then it's in the subset, because that wouldn't make sense. It wouldn't make it a subset. If this ever occurred, I'd have a problem. So for every single location in our mask, we only have 3 possible options. And so this is the number of terminal nodes. And I have 3 options for placing them in terms of the masks. And so what I'm left with is I have 3 to the t, which is the number of ways I can form these masks. So I end up with 3 to the t. And that gives me a runtime of subsets of subsets. There's also another way I can attack this in terms of runtime. If you're familiar with the binomial theorem, what you could do is I could take 3 to the n. I could expand it out. This is into a binomial, so 1 plus 2 to the n. So a binomial you've probably seen before is x plus y to some n. You actually, the coefficients you get here for the binomial are called binomial coefficients, and they are given to you through Pascal's triangle. But here, you can look this up, binomial theorem. One way we can do this is we'll end up getting a summation from I equals 0 to n of n choose I times 2 to the I. And what this is, the summation right here, is imagine me taking all subsets of size I. So that's my master subset. I have n nodes. I'm just going to consider a subset of size I. And then for that subset of size I, there are 2 to the I ways to take a subset of that subset. So I can use binomial theorem to prove the 3 to the n runtime for the terminal nodes. And so that's the DP for computing Steiner tree. It's a really simple DP to code, and you'll be seeing that in a minute when I start solving this ticket to ride problem. So let's look at ticket to ride. So our first example of a Steiner tree problem. So if you ever played this board game, it's actually a board game. You can go buy it and play it yourself. What we have here is railroads we have to form. So we have cities and we have rail lines. And what we'd like to do is we'd like to pair off 2 rail lines. So I might have a rail line of type 1 and a rail line of type 1. Or I might have a rail line of type 2 and a rail line of type 2. And what I'd like to do is, using minimum costs for these rail lines, I'd like to pair these off. All right? So it looks like there are 2 disjoint rail lines that I could potentially pair off. But what's allowed in the problem, so let's say I move my rail lines around. Let's say that this is rail line 1, and this is rail line 1. One potential option I have for pairing things together is to take the Steiner tree and just pair them like this. Well, not really Steiner tree, but pair them together. So this edge is only used once in terms of my railroad, and it's shared between the 2 tracks. But the only thing I need to guarantee is a city from going from 1 to this one, they have to be connected. So in other words, a potential solution to this problem isn't this. I can't connect 1 to 2 and 1 to 2 and call it a day. 1 has to connect with 1, 2 has to connect to 2, and it's given in the problem. And then I can end up solving this because it ends up going together. So one potential solution is like this. One potential solution is just pairing them like this. And the roads have costs that you pay for buying them. So you want them here. Some constraints. So let's look at the number of nodes. Well, the number of nodes is up to 30. All right. Let's look at the number of edges. This is up to 1,000. So we have a small number of nodes, but it's not something we can pure brute force. That's looking pretty bad. And then let's talk about number of railroads. They actually tell you you're going to have exactly 4 railroad pairings that you'd like to form. So 1, 2, 3, 4. And so you'd like to make a railroad network of minimum cost by making these pairings. Pretty good. Okay. So the idea is, if we look back at our Steiner tree algorithm, we can compute all subsets of terminal nodes. What's their Steiner tree? Because that's how our DP works. It's our state of our DP is what node is the root node of our Steiner tree, and what subsets of terminal nodes did we actually hook up. So I can use that intermediate calculation and consider pairing 1 with 1, or consider pairing 2 with 2, or consider pairing the group of 1, 1 with a group of 2, 2, and potentially pair 3, 3, and 4, 4 together. I can handle all those cases because I'll have the subproblem solved, pre-computed, using my dynamic programming of all possible Steiner trees for all subsets of terminal nodes. So pretty cool. So the solution to this problem, I'll just go over it at a high level. Very first thing I do, pre-compute all Steiner trees. So all Steiner trees for all subsets of nodes. Terminal nodes. Step 2. Pretty easy. Brute force or DP. I'm actually going to do this with DP. All pairings of trees. So you're going to do things like, oh, I want 1 in its own group. I want to pair railroad 4 with railroad 3, and then railroad 2 is in its own group. And I'm just going to do all those groupings. So maybe I want 4, 3, and 2 to be in the same grouping, and then 1's in a grouping by itself. So there's all kinds of we can do this. So I have brute force or DP, all pairings of subtrees, and that's how that's going to work. And I just take the best cost. So let's get coding. I want to show you guys how to implement this one. I think it's a pretty cool problem in terms of how I can code it. So that's where I'm going to begin. Oh. I've actually written some code already. So this problem is pretty annoying. All of the nodes and connections and everything are given as strings. And I don't like that. So I want everything as nodes in a graph from 0 to n-1, because that's the canonical graph. It makes things easier to do. So I wrote some extra code here. Basically, I just took a hash map. I took the string, the name for the city, and I just mapped it to a number from 0 to n-1. So I have this getID function. It's lazy. What it does is it looks into the map. If it hasn't already found a name for that string, it puts it in the map and gives me back a new identifier. So it's a pretty helpful function to have here. This problem has multiple test cases per file. So if I ever get the 0, 0 case, I break out. I made an adjacency list, or adjacency matrix for my graph with all the different costs. And I set the identity to be 0 across that whole matrix. And then I just grab all the names. So they give you the names up front. I don't care. I'm reading them in just to make my algorithm consistent with the input. And I read in every single edge here. And then I'm saving the minimum cost of what's already there with this new cost C. And it's an undirected edge, so it goes from I to J, J to I. So I'm doing the minimum cost, so I allow parallel arcs. This way, if I have two edges going in the same direction, I can reuse them. And then I read in the roads. So these are the pairs of roads that I want to form for my train. And subsets of these are going to be in roads here. So the very first thing I'm going to do is I'm going to change this cost matrix to be an all pair shortest path cost matrix. So I'm going to implement Floyd-Warshalls real quick for you guys. It's the very first step I want to do. If you're ever doing a Steiner tree problem, this is just something you're going to have to do if you want to use this slower but more flexible Steiner tree. So it's going to handle, we have 8 terminal nodes in our Steiner tree potentially. So this version of Steiner tree is what we need. We can't use the Spider-Man algorithm. We have too many nodes for our Steiner tree. So so Floyd-Warshalls is I have this for loop structure. I'm connecting I to J, and I consider going through all possible K values. Runs in n cubes. It's pretty great. All right. One thing that is kind of annoying about this problem is we do have these intermediate nodes here. These nodes on the roads are going to be our terminal nodes for our Steiner tree. Well, in order to do a mask, we could have up to 30 nodes in the graph. I don't want to have all possible masks of 2 to the 30. I want to have 2 to the 8. That would be better for me. So what I'm going to do here is I'm just going to take all the relevant names. We can repeat nodes in our railroads, by the way. That's one piece here. So we could have 2 railroads ending in the same node. So it's not a good idea to throw them all together. What I'm going to do is figure out exactly which nodes are terminal. So that's going to go into my tree set. Those are all the terminal nodes that exist. So I can pre-compute how many terminal nodes there are, just right from the tree set. So that's for convenience. I'm just rewriting it in the name. And then I'm going to make this table called group. So I do this for coordinate compression, and I do this for relabeling. If I ever have a case where I want to map numbers from like 0 to 10 to the 9th or 0 to something else, if I want to be able to map from those numbers to just 0 through n, or 0 through a number of terminal nodes, this is what I do. I just run through my sorted tree set, and I just end up making an array where the nth node is the nth terminal node. This allows me to map forward and backward very efficiently. If I want to map forward, I do a binary search on here, and it figures out what index I'm at for this particular value v. And if I want to go from a compressed space, so 0 to number of terminals, to what the actual node is, I just look at the ith element of this table. So it's like I have a map forward and a map back all in one array. It's pretty great. OK, so now we get into the Steiner tree code. So what I'm going to do here is compute Steiner trees. I know what my terminal nodes are. I know what those are. I have to be a little bit careful about how I mark things. So I'm just going to make a table called min cost. And this is going to store my Steiner tree. So if you recall, the state of my Steiner tree for doing iterative DP is what node I'm on and the mask of all the terminals. So I just do n terminal nodes here. So what I'm going to assume initially is everything in my DP has cost infinity initially. If you haven't seen this before, some people, what they like doing is they like writing INF or infinite node. I like writing $00 because it kind of looks like the infinity symbol if you were to join the middle a little bit. So my infinity symbol here, I'm just setting it equal to 987654321. You might wonder why I do that. It's so I can do this. I didn't do that very well. But I can basically slide my finger across the top of the keyboard and type infinity really fast. And if I double this value, it doesn't overflow an int. So that's one thing I like to do when I'm coding. And it's intimidating. So if you're coding in person, you slide your finger across the board, you're making a lot of noise. And it's the most exciting thing that happens in a 5-hour programming contest in ICPC, as far as scary noises distract other people. It's perfectly legitimate because you want to type that infinity value. Okay, so now I need some base cases because I'm going to do a bottom-up DP. And my base case is what node I'm currently on. So I have to look at the ith terminal node. And I'm saying I'm already at that ith terminal node. And my mask, this is completely covered. So this is the trivial case. This is a one-node Steiner tree. That's my base case. And it's just going to have cost 0. I haven't taken any edges to form it. I basically get those for free. OK, so now I run the DP for all possible Steiner trees. I'm just going to run through what mask I'm on. One cool thing, if you've ever done iterative DP, maybe you don't know this. If you run through the DP in order of all possible masks, for every mask, you're going to pre-compute all its subsets before that mask. That's why we can run this iteratively. In binary order, something with bits 1, 1, 0, 1, 1 are everything with, if you take away one of those 1 bits, is going to be computed before that number in binary. So you can run DP iteratively this way. You don't have to memorize it. I'm going to run through all possible nodes. So what I'm doing here is I'm trying to calculate the state I, mask. This is the state I want to compute. So it's the tree I've formed of minimum cost rooted at I, where this mask of terminal nodes has already been joined. That's what I'm trying to compute. So then I loop through all possible submasks. I'll call it subset. I loop through all possible subsets of this mask. So if you want to do subsets of subsets, if you're doing it on masks, this is really easy to code. What I can do is I can loop through the entire mask full. And I keep looping until I get a size 0 subset. So I've completely exhausted everything. To go to from the current subset to the next subset of subset, I just take the subset, subtract 1, and AND it with mask. Really easy to code. So that's subsets of subsets. So SS will be all subsets of mask except for the empty set, given some mask here. So this is really efficient code for doing subsets of subsets, really easy to code. And you can work out why this code works on your own. I won't explain it in detail. Maybe a future episode. OK, so what I'm going to do here is I'm going to take the minimum of what's currently there. And what I'm changing it to. So my new changed value is going to be min cost of I in the subset plus the min cost of I and everything not in the subset. So mask minus the subset. You can also XOR it with the subset, and it'll also find that information. OK, so what I've done is I've basically, using all possible subsets, I've computed all possible subtrees being joined in my Steiner tree rooted at node I. Now what I'm going to do is I'm going to try moving the cost around. So I did a small optimization here, I guess you could say. If I basically found a Steiner tree, so if I had something less than infinity, then what I did is I tried moving the cost around. So that's my next improvement, I guess you could say. And so the cost of moving it around is the cost of being at I and having this mask, plus the cost of moving it to the new node. So what I do is I query my all pair shortest path table, which was cost, and I try moving from root I to root J. So one thing I'd like to point out, just continuing on from where I left off, is some of these submasks are going to overlap edges they've seen or nodes they've seen, and they're not really going to be trees. But the optimal answer, the thing that's stored in the optimal cost for some node J for some mask, is going to be a tree. So even though we might mess up, we might get something that doesn't have this tree formed, the optimal cost out of everything will be a tree for sure, for different roots. So we could end up having, like, we could pick a bad J when we move this cost around, but whatever the optimal cost is for J, after we've moved everything around, it's actually going to have that min cost. And so this is it. This is the Steiner tree DP right here. Nothing very complicated. It's pretty short. The Spider-Man algorithm is actually much harder to code, but it's faster if you have less terminal nodes. If you have more terminal nodes, you have more time, you can do this algorithm. So it's this exponential algorithm here. You also have to deal with that pre-comp n cubed for doing all pairs shortest path before you run it. Okay, so I have a Steiner tree where it's all nodes, subtrees rooted at I. What I'd like is I'd like a table for some number of terminal nodes. And not rooted at I. I just want to know for this mask of terminal nodes, what's the minimum cost to form that Steiner tree? So here's how I'll do that. I'll run through all possible masks. So I try all possible roots, and I just pick the best one. So I get math.min of min total, what's already there, and picking this as the new root. So pretty good. All right, let's do something a little bit better. Now the last thing I need to do to solve this problem is I have to consider combining railroads. So I'm going to run another DP. So the state of my DP is going to be which terminal nodes have I combined. So it's going to be a mask of, well, not terminal, which rails have I combined right now? Like which railroads have I satisfied, yes or no? And there's only 4 railroads. So it's going to be a mask of size 4, so 2 to the 4. You could also brute force this, but personally, I think the DP is actually easier to code. So if you're really comfortable with DP, you can save some time by doing this instead of a brute force, but you could do this last piece as a brute force. The bounds are small enough for sure. So I'll run through every possible mask. And so one thing I want to do is I don't want to try pushing my DP if it ends up having cost infinity. Now what I'm going to do is I'm going to run through all possible submasks to consider taking. So this is my predecessor submask. So I'm going to pick railroads, basically railroads to join together, and then add to my DP8 mask. I'll call it SMASK. So we definitely want to make sure that the things we're adding we haven't already added. So if I end up trying to join 2 things that are together, I just continue. So you might ask what join mask is. Well, based on SMASK, which is a mask of which roads to take, what I'm going to do is I'm going to walk through all those roads that are relevant to this mask. And I'm going to get which terminal nodes I need to join using my Steiner tree to join all these roads together into one big Steiner tree. And that's what I'll do here. So I'll loop through all possible roads. And if this road was supposed to be in my Steiner tree, then what I'll do is I'll get the terminal nodes. So what I need is I don't need the terminal nodes in terms of where they are in the graph. I need them where they are in terms of the terminal ID, that value from 0 to n term minus 1. So that's what I'll do is I'll look at my table. I'll do arrays.binary search. So if you're in Java, you can do this. Or if you're in C++, you can use low bound, perfectly fine. I'll just look through rows I of 0. That'll get me y. And then I'll loop through here, rows I of 1. And so these are the two endpoints of my road compressed to be the terminal nodes. So then I'll just take the join mask is basically just ORing these two things together. So now I get a new mask. All the ones that are going to be in join mask are the mask of things that I need to join together as a Steiner tree. And so now I can update my DP table. So I take the min of what's already at this state, which is mask ORed with mask. And I try improving it by my current mask. So my current mask is whatever's currently in mask. And then I look at my Steiner tree. What's the best Steiner tree I can form by joining these terminal nodes together? And so now my answer is going to be saved in DP. So I just look at DP of all the roads satisfied. What's the minimum cost I had to get all my roads satisfied? Okay, let's take a look, see how we did. We might have a bug, and I'm kind of scared of that. Yeah, we definitely have a bug here. So you have to do some small debugging and try to figure out what's going on. But it compiled first time, so that that wasn't a shame. So it appears to be getting some cost stuff right. So let's take a quick look at this stuff. Try to find out where my bug is in my code. So arrays.toString of CC. I should have been doing a little bit of block testing all at once. Usually when I code these kind of problems, I'll print out intermediate results like this, make sure I'm reading in the input right, make sure stuff's going on so I don't mess up. Maybe I'll print out group, make sure I'm getting that right. Yeah. Yes, it's a DP within DP problem. It's kind of cool. So right now, these are my terminal nodes coming out in terms of my graph. So what you're seeing there, that appears to be working. Let's see if the Steiner tree is coming out okay. Yeah, we'll do it here. This is gonna have a lot of printout, but that's fine with me. I'll do I and mask and min cost I mask. All right. If you haven't seen this before, we have integer.toBinary string. Great for printing out masks. It's a good debug tool if you haven't seen that before. If you're in Java, you get all these fancy toys, except they're really long to code. So Java is very verbose, but it has a lot of toys. So that's the trade-off you have to deal with. Appears to be working there. Ooh. Okay, so here's my bug. Min total. Min total is supposed to be the min Steiner tree. So this is bug number 1. So what I need to do is total with infinity. And that should improve my min total for the masks that I found so far. All right, so let's see if this passes samples. Yeah, it appears to pass samples. I could make more test cases, but honestly, this problem is really annoying with all the like city names and all that kind of crazy stuff. So I'm just gonna test on samples and submit. But you should definitely try to make some test cases when you're doing hard problems like this, or at least try to stress test it or sanity test it, or do a little bit more than I'm doing here. But we're gonna see if I get this correct. So I'm gonna submit this to the good old judge and see what my verdict is. As you can see, so 20 days ago, we had a practice where this problem came up. And so I'm basically resubmitting there. And as you can see, correct, boom. And so that's how you do Steiner tree. It's a pretty interesting, those are the two algorithms I know for Steiner tree. There's some other variations. If you have like 4 nodes, one thing you can do is something a little more brute force. So instead of running the Dijkstra's, you can basically, I guess the last thing I want to say is, and you could figure this out on your own, so I'll leave this as exercise for you. But if I look at the number of Steiner points at any given time in terms of my Steiner tree algorithm, one thing I could do is I could brute force where the Steiner points are, and then use my single terminal shortest path and all pair shortest path to basically combine them together based on all cases of the reduced tree. So here's my last Steiner tree algorithm before we go, is I could just brute force the Steiner points. So maybe I'll draw those in blue. So in this case, one thing I could do is the Steiner points, I just pick pairs of nodes I and j, use all pair shortest path to compute here, hook up some subset of nodes here, some subset of nodes here, and then join them that way. So I've seen problems where that's the algorithm you want to use. It's one of the easiest to code, but if this DP that I just showed you worked, you saw that the DP for Steiner tree is not that long. This is actually a pretty useful way of computing Steiner tree. It doesn't take much time. Okay, so I did get another question. They were saying, can you comment about your hardware to write, etc.? So I definitely want to answer that question. So some people are wondering about my setup here for running algorithms live, what I'm doing, how I'm able to make all of this work. So one thing is I have a Surface 3. I guess it's Surface Pro 3. And that's what I'm using to write my code and also to draw. So that's my hardware side here. And the software I'm using to do some of my notes for Algorithms Live, that's OneNote. So just Microsoft OneNote. And I like it for, there are other tools I could be using to draw, but one of the reasons I'm choosing OneNote is I've got this very minimalistic palette up here to do some of my drawing where I can change colors, do stuff like that. And OneNote is a really good choice for that. And I basically get full screen as I go. And yeah, that's basically it. And on the recording side, I'm just using Google Hangouts. That's why you see that Google logo in the top left corner of Algorithms Live, if you haven't noticed it before. So they do a watermark if you're using it for Hangouts to do your broadcasts. But that's what I'm using. And let's see, anything else? Just have a simple keyboard setup hooked up to my Surface. Yeah, and so it's a pretty minimal setup. I'm using a headset for talking to you all. And so the headset's good when I have guests, I can hear them and that sort of thing. So definitely, if you get the chance, tune in on Sunday, because we're going to have RNG 58. and that's Makoto Sejima. And we're going to talk about @coder. We're going to talk about one of his really cool problems. And I'm preparing every possible way possible not to have technical difficulties this week, because that was a shame to have to cancel last week's episode. But really looking forward to this one. I think he's going to be a great guest. He is my favorite problem writer in programming contests. And if you haven't tried this problem, 9270 on @coder, it's just really cool. It's just simple. The solution is mind-bogglingly elegant, and it's a really difficult problem. And so definitely give that one a try before we talk about it. Yeah, Makoto is definitely brilliant on these kind of things. And I know a lot of you had some really great questions for him, and those are things we're going to discuss on Sunday. So definitely tune in on Sunday for our second Algorithms Live episode. And so thanks for tuning in, everyone. I'll see you guys on Sunday. Watch that one live or watch it in the rerun. The stream will be available after. And I'll see you guys next week. I do want to talk about next week as well. I'm going to start going into convex hull optimization and techniques for data structures. So that's where I'm going to be headed after the RNG 58 episode. And discussing @coder. So we'll see you guys all on Sunday. Hopefully you can all tune in. That should show up on my channel soon. And then next week, we're just going to dive right in, and we're going to solve tons of problems involving convex hull optimization. I think it's a really cool technique. And we're going to look at different ways to approach data structure problems in general. So can't wait. Please tune in on Sunday. See you guys all next week.